What is the Doppler effect? The Doppler effect is a change in frequency or wavelength of a wave in relation to an observer who is moving relative to the wave source.
Hello and welcome. My name is Eric and I'm here for us to take an intuitive peek into the Doppler effect formula. By the end of this video, you should be able to answer more than 100 MCQs in 60 seconds or less. Here's a little caveat to that though. Those questions must be aimed at testing your understanding of the formula and how to use it. And also at the end of the video, you will come to a realization that this was a lot easier than you thought. So right away, let's begin. Think of a fraction. What happens to its value when you increase or decrease its numerator or denominator? A fraction's value is directly proportional to its numerator, meaning if the numerator goes up, the fraction goes up. If the numerator goes down, the fraction goes down too. However, the opposite is true for a fraction's denominator. A fraction's value is inversely proportional to its denominator. So, if the denominator goes up, the fraction's value goes down. If the denominator goes down, the fraction's value goes up. You might want to ask why this is important at all to our mission. Okay, here's the Doppler effect formula. Oops, no, not that one, this one. F prime is the apparent frequency, which is the frequency perceived by the observer. F is the actual frequency, which is the true frequency emitted by the source. And this is where our fraction comes in. The fraction contains V, Vs, and Vo. V is the speed of sound, Vo is the speed of the observer, and Vs is the speed of the source. This part is what determines whether you hear a louder sound or not. Whether to put a minus or a plus in the numerator or denominator is entirely dependent on rule number 1. If it is approaching, then it is contributing to an overall increase in the fraction's value. Rule number 2, if it is receding or moving away, it's contributing to an overall decrease in the fraction's value. If you understand this, we are ready to go. This, in addition to the knowledge of how a fraction's value is affected by its numerator and denominator, are two powerful tools you would use to answer every question on Doppler effect formula. The purpose of this is to help you not memorize but interpret every scenario accurately and compute the apparent frequency. We are going to examine 4 cases or scenarios. Scenario number 1. When both observer and source are moving in the same direction, but the observer is leading. To put it simply, the source is chasing the observer. Imagine on a road we have a car blowing a siren and following an observer who is also moving in the same direction. So in that case, how do we compute the apparent frequency? Take a look at the formula again. Do we put a plus on the top and a minus on the down, or a plus on the down and a minus on the top, or both pluses or both minuses on top and down? That will be determined by the 2 rules I gave you. Now back to our first scenario. Since the observer was receding, the observer is causing a decrease. And you know that the speed of the observer is in the numerator. So, in order to decrease the overall value of the fraction, we need to subtract. So that's why we are subtracting. And since the source was approaching, we need to increase the overall value of the fraction. So in order to increase the overall value of the fraction, we have to decrease the value of the denominator. And so we have to also subtract in the denominator. Okay, let's look at the second scenario. The second scenario is when the observer chases the source. That means that the source is in front and the observer is following, and they are moving in the same direction. Starting with the observer, is it approaching or receding? It's approaching, yes. So it is supposed to cause an increase in the overall value of the fraction. But as we already know in the formula, the velocity or the speed of the observer is always in the numerator. So we need to add it. We need to use plus v plus vo. Now let's go to the source. Is the source receding or approaching? It's receding. So since it's receding, it's causing an overall decrease in the value of the fraction. And as we already know, the speed of the source is always in the denominator. So in that case, we need to add it up so that the denominator becomes big for the fraction to become smaller. And that is why we are using plus. And for our third scenario, we have both of them approaching each other. We have the source approaching the... Let's start with the observer. The observer is approaching, so it means it's causing an overall increase. You will hear a louder sound. So since it's causing an overall increase, we have to add in the numerator. Next, let's go to the source. The source is also approaching. So it is causing an overall increase in the apparent frequency. So you will hear a louder sound. And to increase the overall value of the fraction, we have to decrease the denominator by subtracting. And that's why we are using minus in the denominator. And for our last scenario, we have both of them receding or moving away from each other. So let's start with the observer. Observer is moving away, so causing an overall decrease in the apparent frequency, making the sound less loud. So in the numerator, we subtract. Let's go to the source. The source is moving away too, so causing an overall decrease in the whole fraction. So if we want an overall decrease in the whole fraction, we have to increase the denominator. So in order to increase the denominator, we add the velocity of the source to the velocity of the sound. This gives us v plus vs. Okay, let's take an example. A train is moving at 40 meters per second and sounding its horn at 280 hertz. A car is driving towards the train at 25 meters per second. What frequency does the driver of the car hear? Take a moment to think about what this case is. Is it one chasing the other, both receding, or both approaching? If you follow the right thought process, you would arrive at both approaching. So we would all agree that the train is moving towards the car and the car is also moving towards the train, so causing an overall increase from both sides. We are going to take the speed of sound to be the speed of sound at room temperature, which is 343 meters per second.
When you have all the information like this, what you need to do is substitute the values of the variables, the velocities and the frequencies there. We're finding the apparent frequency, so that one is not there. You just write it and say equal to, then you put 280, bracket open, then you put the velocities at their various positions. We know the velocity of sound to be 343, so it will take its position at both top and down of the fraction. And we also know that the velocity of the car is 25 meters per second. It will take its position at the top, the numerator. And we also know that the velocity of the source, which is the train, is 40 meters per second, so it will take its position in the denominator. The last piece of information you need is to figure out whether there should be a plus or minus on the down or top. So let's do that. So we know that the observer was approaching. So since the observer was approaching, that would mean that it's causing an overall increase in the value. So we would look for a way to increase the numerator, because an increase in the numerator automatically means that there is an increase in the fraction. So we'll add in the numerator. So we'll put a plus on top. The opposite is what we would do in the denominator. We put a minus, because if we want the fraction to be bigger, then we have to make the denominator smaller. And with this, we are done. The rest is just computation. If you compute this value, you get 340.066 hertz.